So very good morning, children. We'll start the session. So this is our fourth session in dual nature of radiation. First, before what we discussed, just we'll revise quickly. So in last class we discussed about the some few graphs, that is two graphs we discussed, and experimental verification of Einstein photoelectric equation, okay, and Millikan change in that one, and then graph. So the graph between the stopping potential to frequency. So we discussed about experimentally verification of Einstein photoelectric equation. So that the topic is finished. Okay, just revise it. It's a very important topic, that one. Okay, and most of the numericals they will ask from based upon this photoelectric equation or Einstein photoelectric equation, and this is the numeric assignment. So regarding numericals and as well as theory assignment we said, just try to solve it. And the last session of this chapter we'll discuss a few important numericals, okay, which is important for both competitive as well as PU. Okay. Now we'll start our session. So we left with the two topics. So still we have to discuss the two more topics. One is as of now we discussed about the matter waves, that is dual nature. So the topic name is dual nature of radiation and matter. So we discussed about photoelectric emission and everything, some experimental Einstein equation. So this is finished. Now we'll start with that. What is dual nature of radiation and matter? Okay. Now, as we know that light. So what is light? It's electromagnetic radiation. Electromagnetic radiation. Okay, light consists of what? So light consists of photon, that everyone knows. What is photon? So it's just photon, nothing but radiation with the matter. Okay, the radiation with matter which made up of the particles. That is called photon. So we know that group of photons, that is light emits the photons. Every photon has some energy. That energy of photon depends upon its frequency. That we know clearly. We know that. Okay. Now coming to the topic. So dual nature of radiation. First we'll go discuss with the particle nature. So what is dual nature? Both particle and wave nature. Wave nature we'll discuss after this one. So first we'll discuss the particle nature. So and this also will called as a photon structure. We are discussing about particles. That is what photons. Okay, which are moving with the velocity of light. Okay. So what is photon? What is the properties of photon? And it's also called photon structure. Photon structure. Let's discuss properties of photon. I'm writing as a properties of protons or structure of the proton. Just it's a theory parts, make a note of it. So we don't have any derivations except on experimental verification of waves. So as of now, we discussed about the derivation part in last class, but this is only theory part of photon structure, photon properties. So what is photons? So it's made up. Photons are nothing but the radiation with the matter made up of the particles. So matter, this is some amount of matter. So matter nothing but some mass. Okay. But we are not discussing detail about it. We are going through the properties of the photon. Okay. What are the properties? Generally, we know that electrons, protons, not photons, protons and neutrons. So these are massive particles. Electron has some amount of mass, and proton and neutron has some amount of mass that we know. What about photon? If photon has mass, what will happen? When the light falls on us, we will feel some amount of pressure or force, because if massive body, if you assume that photon has some amount of mass, the massive body falls on our body, then we will experience some force, but we are not feeling that. So that is, the photon rest mass is 0. First we'll start with the mass. What is photon and what is the nature of the photon? How photon will behave in electric and magnetic fields? Everything. Okay, just point by point we will discuss. First one. neutral in nature. Neutral. So as we know that positive charges and negative charge. Electrons has a positive charges, protons has electrons has negative charges, protons has positive charges. When this charge is placed in a electric or magnetic field, the charges will experience some force. That way. Neutral. Neutral means what? It doesn't have any charge on it. So that is the it said photons are nothing but neutral particles. Neutral particles. So it doesn't have any charge on it. Photons. So that's why first neutral nature. Neutral nature. So as having of neutral or charge, neutral, that is zero charge, almost zero charge. Or neutral is nothing but equal amount of positive and negative. So finally the net amount is zero charge. Okay. So neutral in charge, there is no charge of a proton. If the photon passing through the fields, electric as well as magnetic fields, what happens? It doesn't experience any force because it doesn't have any charge. So if when any charged body enters into the fields, then only it experiences the force, but it doesn't have charge. So no deflection. So make a note of it. First point, photons charge zero charge. Okay, or neutral charge. Okay, the nature of the charge of the photon is zero. Okay, neutral charge. Okay, so there is no deflection of the photon. Okay, in both electric as well as magnetic field. E represent that electric field. B represent that magnetic field. Okay, so that is as a having of zero charge or neutral. So there is no deflection in electric as well as magnetic field. Okay, when only charged particle experience the force in electric and magnetic field. So no charge, so no deflection, both electric and as well as magnetic field. Okay, that we know. Next, coming to energy. We know very well energy of photon is dependent upon what fact? Frequency. So the energy of photon we are taking it as a h nu. Energy of photon. So h is a Planck constant and nu is the frequency of the radiation or photon radiation. So E is equals to h nu. So that is. Now this is energy. Now coming to momentum. Okay, momentum. Because what we said, the radiation with the matter, so made up of particles. When the particles are moving, so it consists of some amount of, let us assume that m is the mass of the photon, let us assume. So it's moving some velocity, so there is a momentum. So how to find momentum? So momentum generally we are indicating with the p, small p. So what is momentum? It's a product of mass and velocity. So photons, what is the velocity of photons? So photon almost it move equal with the speed equals to velocity of light, because light is radiation. Okay, radiation. So what is the velocity of light? 3 into 10 to the power of 8. So photon also moving with the velocity or speed equals to velocity of light. Okay, so we can write it as a m into c, or another term. Okay, in another term, so we can take it as a h nu divided by c, or one more term, h by lambda. How it comes, we will discuss. Okay, how it comes. So de Broglie wavelength, in case of de Broglie wavelength, we will discuss how this momentum and this equation will comes. Okay, so momentum of photon is equals to mass and velocity is equals to h nu, energy by velocity is equals to h by lambda. So because we know that frequency divided by velocity of light nothing but 1 by lambda, c by nu is equals to lambda, like that. Okay, this make a note of it. We will discuss detail regarding this. Okay, so this is the second property, energy of the photon. Okay, next coming to power. Okay, photons moving with some amount of energy. Okay, so when this energy falls on, okay, or this energy emitting, so not only single photon will come. Okay, so few number of photons will passing through the medium. Okay, the number of photons, let us assume the small n is the number of photons. So the total, each photon has the energy h nu. So let us assume that n number of photons. N number of photons, okay, having how much of energy? Ne. N is the number of photons, E is the energy of each photon. Okay, this is total energy of the total photons. Okay, divide by. Okay, divide with. So if you take time, so T is a time. So Ne is the total energy by time. So energy by time, that gives what? Power. So make a note of it. It's indicated with capital P. So momentum we are indicating with the small p, but power we are indicating with the capital P. So Ne divided by T. N is the number of photons, okay, emitting for every 1 second. So T is the time. N by T nothing but number of photon per unit second, and E is the energy of each photon. Okay. So please make a note of it. First point is, so neutral in nature, so no deflection in both electric as well as magnetic field. Second one, energy of each photon is h nu, where nu is the frequency of radiation, h is a Planck constant, and momentum of the photon, so mass into velocity or speed, okay, in mc or h nu by c or h by lambda, that we will discuss later. Next, power of the photons. If n number of photons emitting per second or moving per second, okay, then Ne divided by T, where E is the energy of each photon. So these are 3 points, make a note of it. Then we'll go for next point. Intensity. Intensity, that is, as we know that light has intensity. Okay. So how to measure the intensity of light or photon or radiation? So intensity. Let us discuss the 4th point. I'll remove it. The 4th point, intensity. As we know that what is intensity? The energy incident for unit area per unit second. Okay, that is general definition. And in another term, it is intensity of photon or radiation. Intensity, that is capital I, is equals to power per unit area. Power per unit area. What is power? Energy per unit time. Okay, and also we can take it as N capital E divided by T into A. So as we know that Ne by T is equals power. A is a cross section area. So the number of photons incident for unit area for every 1 second. The total energy. E is energy, N is the number of electrons per unit second and unit area. So these are intensity equations. So very important. So numerically it's very helpful. Okay. So P is the power of the radiation, A is the cross section area. Otherwise Ne divided by T is the time, A is the cross section area. So please make a note of it. Intensity. Now, how the energy of photon depends upon what factors? So as we know that, what is the formula for energy? Energy is equals to Planck constant h and frequency. It's only depend upon frequency because Planck constant is constant. Okay, h nu. So h is constant, nu. Energy of photon only depends upon frequency. It not depend upon intensity. Make a note of it. So the energy of photon only depends on frequency of the radiation or photon radiation. It's not depend upon intensity. Okay, that's remember it. Okay, so it not depend upon. Next one. Okay, fourth one. Energy directly proportional to frequency. Just make a note. Energy directly proportional to frequency. As increasing the frequency, energy of photon also increases, and it's a independent of capital I. I am writing as capital I. In short form, I am written mentioned as I, but I is what? Intensity. It depends upon frequency and it is independent of intensity. Okay, make a note of it. Next, 6th point. So photons rest mass. Okay, what is rest mass? What is actual mass? So according to Einstein relativity theory, so if any particle of having mass m, and it's moving with the velocity v, so Einstein given the equation that is m is equals to m naught, that is which is rest mass, divided by root over 1 minus v square by c square. We know everything. So Einstein relation it is. Okay, mass of the particle which is moving with the velocity v is equals to m naught divided by root over 1 minus v square by c square, where c is the velocity of light, v is the velocity of the particle of mass m. Okay, according to this, what is the rest mass formula? M naught is equals to m, mass of the particle, that is nothing but photon, it is 1 minus v square by c square. So this is a rest mass equation. M naught is equals to mass of the photon root over 1 minus v square, velocity of the photon divided by velocity of light. But we know photons, nothing but light, moving, photons are moving with the velocity or speed which is equals to velocity of light. Okay, that is v is equals to c. When you are keeping off v value as a c, then c square by c square, it is what? 1. So here subtraction, 1 minus 1, 0, root over 0, 0, 0 multiplied m, 0. So that's why the rest mass of the photon is 0. This is the sixth point. The rest mass of the photon is 0. So according to Einstein relative theory. Okay. So remember this point, the rest mass of the photon is 0. Got it now? So here, as of the 3 years old, and fourth point, what intensity we discussed. Fifth point is how energy depends on frequency, how energy independent of intensity. Okay. And then rest mass of the photon is 0. I am coming to the last point. Okay, it's theory points, please make it. Okay, when a photon, okay, so last one, when a photon passing through the different mediums, air, water or any glass or something, what happens? Just like a light, okay, when the light, if you take the red color laser light, when the laser light passing through the different medium, like taking the water, okay, and just like aquarium. If you take aquarium consists of glass plate as well water, again glass and air. Okay, these are 3 different mediums are there. When the laser light passing, okay, we are making to pass through the aquarium. So the outcome that is the outcome layer laser also having the same color. Okay, that is there is no change of color. There is a change of color. That is your frequency will not change. Okay, frequency will not change. So when the photon passing through, make a note of it please, when the photons passing through the different mediums, okay, so the velocity of the photons changes. Velocity of photons changes in different mediums. So only velocity will changes, so no change in frequency. Remember it, once again I am repeating. So last point, when the photons passing through the different mediums, okay, the velocity of the photons will changes. Velocity of the photons will changes due to change of wavelength. Due to change of wavelength. I'll write one. So we know that E is equals to h nu. E is equals to h c divided by lambda, because nu is equal to c by lambda. Remember it. So which are constant? H is constant. Okay. Okay, when the velocity changes, then what happens when the photon is passing? Okay, it is in air. It is in air. When the velocity, when the photon is passing through the different medium, not in air. So like water or glass, any surface. Okay. What happens? The velocity will change. It's not moving with velocity of light. It changes with v. Okay, it is in air. I assume that it is in air. In medium, EM I am writing, H, the velocity will changes as V and wavelength. Okay. So as we know that H is constant. Okay. But what I am saying, when the photons moving, passing through the different mediums, there is no change of frequency. So as the frequency remains constant, the energy of photon also constant, because we know that. Okay, as the frequency remains constant, this total remains constant, that is equals to energy constant. So energy will never change. But coming to this equation, what is this? H into velocity by wavelength. Okay. So when a photon enters into the one medium, what happens? Velocity will changes. As the velocity changes, hv value will changes from numerator value. So that, but the wavelength will decreases. Okay, same. As a, okay, not decreases, it changes. Okay, decreasing, increasing depend upon the medium. Okay. So as changing of velocity, wavelength also changes. So both numerator and denominator values are changes equally. So the energy remains constant. Remember this point. So when the photon moving through the different mediums, velocity of the photon changes due to change of wavelength. Okay, velocity will changes due to change of wavelength, but there is no change of frequency. So energy of photon is equal in any medium. Got it? So this is a point. This is about photon properties or photon structure. Next we'll this particle nature also with the radiation and photon is a part of the radiation. So particle nature, how photon behaves as a particles. Okay, so the energy and everything. Now coming to particle nature, what is particles? As we know that light has dual nature, particles as well as waves. When we see the particle nature in case of light, okay, I'll start with the example. I have some bunch of balls, okay, 100 amount of balls. Okay, so there is a flat surface. Okay, so I am throwing that balls towards the rigid surface. What happens? The balls are moving with velocity. Just assume that these balls are nothing but photons. Light, okay, the part of the light is photons. When the balls are moving towards the surface, okay. So when these all balls hit the surface, what happens? Due to that rigidity, so balls will reflect. Okay, here we are, all balls are just like particles, that is photons. So here in case of reflection and refraction, we will see the particle nature of light. We will see the particle nature. Reflection, refraction case, we will see the particle nature. Okay, and wave nature, where we will see the wave nature. So in case of interference, so as we know that already you studied waves chapter in first PU. Interference, the two waves are interfere each other. So there is a redistribution of energy. So energy may increases, energy may decreases. It depends upon pace, how they are moving. So like if the two waves are interfering, so they will see some interference pattern. So dark and bright fringes. Okay. So that is we call interference. So in case of interference, so the light behaves as a wave. Next, diffraction case. Diffraction. So these are the 5 properties of light now. Reflection, refraction. In these two, reflection, refraction, in these two phenomena, we will see the particle nature of light. And remaining 3, interference, diffraction, polarization. In case of interference, diffraction, polarization, we will see the wave nature of the light. Wave nature. Okay, interference, two waves are interfering. Diffraction, bending of light at the sharp edges, that is diffraction. Polarization, so changing of direction. So, but in case of polarization, we will see the electromagnetic nature of light. So, electromagnetic wave nature. Again, it is wave. So, this is a wave nature. Light is a nothing but wave. Okay, let's see. First, we will who given this proposal. Okay, or who discovered about experimentally verified the wave nature of matter. So, we are not discussing about light. We are discussing about radiation. So, as we know that radiation is a bunch of particles which have the mass. Okay. First, I will start with the point de Broglie statements or de Broglie hypothesis or what de Broglie proposed. Okay. So, this is a photon properties or particle nature of the radiation. Now, coming to next topic, wave nature. Wave nature of the radiation. So it's better to start with the de Broglie statements. What de Broglie state? De Broglie given 2 statements. Okay, what is that statements? Okay. So what he said, what he proposed, and first he said that so the universe consists of matter and radiation. Understand? The universe consists of matter and radiation. Excuse me, just there is a technical problem. Please wait. Okay. So, okay. We'll start it. So, de Broglie statement. What de Broglie states? So, universe consists of matter as well as radiation. Matter nothing but which are having mass. Radiation, that is light, So that is, everyone knows that matter and radiation. Universe consists. Okay, and when the radiation has a dual nature, if radiation has a dual nature, so the matter also has a dual nature. So these are 2 points he explained. And what is that? Universe consists of both matter and radiation. Second point, if radiation has a dual nature, matter also has a dual nature. And this experimentally verified. So that is what matter is. So radiation has dual nature or radiation has a wave nature. Experimentally verified by Davison and German. That is our last topic. So experiment wave nature of the for radiation, experimental verification by Davison and German experiment. Okay, so that is we'll discuss. Now coming to, he given one statement on matter waves. What is matter waves? Matter waves also called de Broglie waves. Matter waves also called de Broglie wave. He only proposed it. What is matter waves? Okay, matter nothing but some amount of mass. If let us assume some amount of bunch of balls, okay, so moving with some velocity, okay, towards one target or anything. So these massive particles are moving towards or passing through the medium. So this, if you see this one, massive particle, it's not a light, it's a massive particles are moving with velocity, so it has some energy and some momentum. Okay, so these, if this nature, this beam shows the wave nature, so that we call matter waves. The matter wave is nothing but the matter wave which is having matter, that is a group of particles having matter, nothing but mass, small amount of mass, not in like cages or something. So it's some few amount of matter. Let's see electrons, protons, neutrons. Beam of electrons, what we call cathode rays. So cathode rays are nothing, not it's a radiation, electromagnetic radiation. But it consists of what? Electrons, beam of electrons. So many number of electrons are passing from cathode to anode. So that we call cathode rays. Cathode rays we call as matter rays. Okay. In the same way, the protons are moving. Group of protons are moving. Okay, in a straight line. Okay, that waves in wave nature. Okay. So that also we call it matter waves as well as neutrons. So electron, proton and neutron exhibits the dual nature and behaves like a particle as well as waves. Remember that electrons, protons and neutrons. Okay, so they behave like shows the dual nature. These 3 shows the dual nature and they behave like a particle as well as waves. Okay, so this we can take an example of matter waves. Now we'll start with what is okay, we discuss about matter waves. Now de Broglie wavelength. So before that, okay, before discussing about the de Broglie wavelength, so because what we are saying, radiation has a wave nature. So due to the wave nature, so it has some wavelength. How to find that wavelength that matter waves? Wavelength. So that we will discuss now. And wavelength of electrons. If the electrons are moving in a group, deuterons, alpha particle, that is helium nucleus. Okay, so in that case, how to find the wavelength? Okay, let's see. Einstein, that is de Broglie wavelength equation. I am deriving the derivation of de Broglie wavelength. Derivation of de Broglie wavelength. Because what we are saying, the matter waves show the wave nature, so the particles show the wave nature, so it has some wavelength, so we need how to find that wavelength. So we know that, so let us assume that some electrons. So we will take the discharging tube example, cathode rays. So the cathode electrons are emitting from the cathode moving towards the anode. So because the electrons are emitting and moving towards anode, because anode has a positive potential. And when we apply the potential difference between cathode and anode, okay, these electrons, the ejected electrons accelerating because of applied potential. Got it? This just to revise it. Remember this one. What we discussed in first class, discharging tube, cathode, anode. So connected with one potential. Due to this potential difference, so the ejected electron from the cathode moving towards the anode. Okay, because it has a positive potential. Okay, so these electrons are accelerating, okay, towards anode because of applied potential V. Okay, let's just remember it. Let's start. So what energy? Let us in photon energy. Okay, photon, nothing but particle having the mass. Okay, so the energy of photon according to, okay, so quantum theory, the energy of the photon E is equals to h. And we know that if any photon has mass m and it is moving with the velocity c, moving with the velocity c. So massive body and having the velocity c. So it has kinetic energy according to Einstein energy mass equation. According to, see, first one is we written energy of the photon by using quantum theory. Now Einstein energy mass theory, everyone know this one, E is equals to mc square. Even non-science student also know this. E equals to mc square, where m is the mass of the photon and c is the velocity. Okay, so these both are same, both give the same energy of photon according to quantum theory, energy of the photon which has a mass m and velocity v according to Einstein equation. When you are comparing this, mc square or h nu or, okay, alright, h nu is equals to mc square. Okay, nu is what? Frequency. Frequency is equals to c by lambda. You know that. Frequency equals to velocity by lambda. So hc divided by lambda, that is equals to mc square. Take it out. What we get? H by lambda, that is equals to mc. H by lambda, that is equals to mc. What is? So h by lambda is equals to mc. Okay, take this mc here and lambda, that's it. Then lambda is equals to h by mc. H by mc. So the wavelength of the particle is equals to h by mc, where m is the mass of the particle and c is the velocity. So the velocity or speed is equals to velocity of light for photons. Okay, this also we can take it as h by p. H by p. So please make a note of it. So derivation of de Broglie wavelength by using quantum theory as well as Einstein equation. According to, once again I am repeating, just please make a note of it. Energy of photon E is equals to h nu according to quantum. So energy of a photon which having the mass m and moving with velocity c, according to Einstein energy mass relation, E is equals to mc square. Equation number 1, equation number 2. From both 1 and 2, both are use the same meaning. So h nu is equals to mc square. So nu is equals to c by lambda. Frequency equals to velocity of light by wavelength. It's c by lambda is equals to mc square. Here c and f, one c will get cancelled. So what is the remaining term? H by lambda is equals to mc. Okay. So m is mass and c is the velocity. That is velocity of the photon, mass of the photon. So which gives the momentum. Or lambda is equals to, okay, so interchange this mc and lambda, then lambda is equals to h by mc. H is a Planck constant, m is the mass of the photon and c is the velocity of the photon, which we call as a momentum of photon. Okay, so we take as a h by p. H by p. So please make a note of it. We'll move forward into the another important equation. Okay, please make a note of it. So de Broglie proposed that are given the definition for the materials. Then how practically or experimentally verified? Okay, that is de Broglie given the equation. So how lambda becomes what is the wavelength? So let wavelength of the matter waves, that is h by p. Is it practically proves? Okay, so then practically or experimentally? Okay, theoretically we have few values for the some electrons, protons, something. So when the electrons are moving with some moving in a medium, so the what we call the matter waves, the electron has some wavelength that is equals to 0.167 nanometer or 1.67 nanometer. That is what theoretical value or expected value. Sorry, not expected and theoretical values. Okay, and proposed values also we can take. But experimentally, is it correct? So experimentally also we need to prove that. Okay, we'll see. So next topic. We'll continue with lambda. So what de Broglie wavelength? Lambda is equals to h by here p is a momentum. Okay, momentum of what? Photon or electrons or any matter particles which has a mass or matter. Okay, and we know that energy and momentum relation. Okay, see here kinetic energy, as we know that kinetic energy is equals to p square by 2m. So in first year you will see that this work energy theorem, okay, or work energy chapter, kinetic energy equals p square by 2m. So from this one, p is equals root over 2 into m into kinetic energy. Okay, just remember it, momentum. Okay, now what I said, just imagine the discharging tube. Okay, when the charged particles, when the cathode rays, that is beam of electrons. So beam of electrons, that is electrons has mass. So we consider these a beam of electrons as a matter waves. Okay, so when the electrons are moving from cathode to anode, okay, so through the medium, okay, it exhibits the wave nature that we know. So the electrons are, why it's moving from cathode to anode? Because of potential difference. So the electrons has which energy? It accelerating, so kinetic energy. Okay, so that kinetic energy is equals to QV. I said that already, the energy is here already here. The kinetic energy is equals to charge into V. So already during stopping potential concept we discussed about it. The kinetic energy equals to charge of the particle. What is the charge here? Instead of Q I am writing E. E is an electron charge, that is 1.6 into 10 to the power of minus 19 coulombs. Here V is what? Potential difference applied between anode and cathode. Already we discussed this. Okay. Okay, those who missed this topic, just see the previous videos. Then you will come to know that from why I am writing kinetic energy is equals to EV. Okay, QV, W. Q is a charge and V is a potential. Here charge is nothing but charge of electron, that is 1.6 into 10 to the power minus 19. V is what? Applied potential. So replace this kinetic energy with E. Replace this kinetic energy. So therefore, momentum P is equals to root over 2 into m into, okay, instead of kinetic energy what I am writing? EV. Momentum. So therefore, if you write this P value in de Broglie wavelength equation, lambda is equals to Planck constant h by, what is P momentum? So you can write in kinetic energy term, you can write in this term, because we are using this one because experimentally we need to verify this. So in experiment we can't calculate the kinetic energy directly, so we can easily calculate the kinetic energy by knowing of potential. Okay, so that's why I am writing 2 into m into EV. So very important equation, lambda, that is wavelength of de Broglie wavelength or matter waves. The wavelength of matter wave lambda is equal to h by 2m EV. Here m is what? Mass of the particles. If you take electrons, you should apply the mass of the electrons, charge of electron. If you take the protons, mass of the proton, mass of this one. Only charge it is. Okay. So those who can, that is the particle which can accelerate it due to potential, only protons and electrons. So in that case, and deuterons, alpha particles, you can consider these things. Okay, let's see. H lambda is equals to, So wavelength lambda is equals to h by 2m into eV. Okay. Now, how this lambda, that is de Broglie wavelength for different particles. So please make a note of it. I am giving a few important equations. So which is sometimes useful in shortcuts. Okay. So wavelength. Okay, wavelength, de Broglie wavelength, general formula h by 2m into U. Okay, if you take the beam of electrons, okay, for electron, the de Broglie wavelength for electrons. So during the electron, what we have to substitute? H value 6.62 10 to the power minus 34 and 2. M is what? Electron mass 9.1 into 10 to the power minus 31. E, charge of electron 1.6 into 10 to the power minus 19. We don't know. So by substituting of M value, E value and 2 actually and H value, you will get that, okay, one fixed value. So that is, remember it, for electron, the wavelength of electron 12.27 divided by root V. The potential we don't know, that's why I am writing here like this. V is the applied potential difference. V is the accelerated potential. Okay. So in angstroms, you know that what is angstrom? 10 to the power minus 10 meters angstrom. This is for electron. So in the same way for protons. In case of proton, what we will do? We will take it as a mass of the proton and charge of the proton, that is same 1.6 into 10 to the power minus 19. Only mass will change. Okay, 1.6 into 10 to the power minus 27. Okay, by substituting of mass of the proton, charge of the proton, everything. So what we get here, de Broglie wavelength for the protons, it is 0.286 divided by root V angstroms. Please make a note of it. In the same way, deuterons, you know that H12. Okay, and so in case of deuterons, substituting of mass of deuteron, charge of deuteron, so then you will get that the wavelength is 0.202 divided by root V angstroms. 0.202 root V angstroms. Okay, this is okay. Now coming to the alpha particle. So we know that alpha particles are nothing but helium nucleus. So which has a mass twice of the deuterium. Okay, that is helium-24. Okay, so mass is double than H12. So then by substituting of mass of the alpha particle, charge of the alpha particle and charge also double. So then you will get that 0.101, here 202, here 101 divided by root V angstroms. So remember that, so in denominator root V is constant, we don't know the accelerated potential. So in numerator for electron 12.27, for proton 0.286, for deuteron 0.202, for alpha particle 0.101 in angstroms. Okay, you can convert it into nanometer also, but better to remember in angstroms. So very useful when you apply the lambda in angstrom. So that we will discuss later. So this is a wavelength. Clear now? So this is what we discussed today. Just once again, what we discussed today's session, I will revise it. We started with dual nature of radiation. What is radiation? The radiation. First we started with the particle nature of the radiation. So what is in that photon? We discussed about photon. What is photon? The radiation with the matter made up of the particles. Okay. Then we discuss about the photon properties, energy of photon, momentum of the photon. Okay. And intensity. So how the energy of the photon depends upon frequency. How it is independent? It's independent of intensity. And next, rest mass of the photon is 0. And the same way, the velocity of the photon is different in different mediums because of change of wavelengths. Because change of wavelength that we discussed, that is photon structure. Then followed by the wave nature of radiation. So in that de Broglie statement, so de Broglie stated that universe consists of the matter as the radiation. If radiation has dual nature, matter also has dual nature. Then we derive the equation of de Broglie wavelength lambda h by p. So then followed by what is P? P is in terms of kinetic energy, P is in terms of accelerated potential P. Okay, by substituting you will get the one common general equation for the de Broglie wavelength. So the de Broglie wavelength is for electrons, protons, deuterons and alpha particles. So please make a note of it, you have to revise it. Okay. So then the last topic we will discuss in next session, that is what? Okay, matter waves or de Broglie waves. Okay, we should experimentally verify. We should experimentally verify this de Broglie wavelength. Okay. So this we have this much by substituting of E value, electron has some wavelength. So that wavelength, theoretical wavelength. So we have to prove by experiment. Okay, that is not we have already is proved. We need to discuss that one. Okay. So that is what Davison and Germer experiment to prove the wave nature of the matter waves. Davison and Germer experiment for the to prove the wave nature of the matter waves, de Broglie waves. Okay, that we will discuss in next session. Please revise it. Okay, so please revise it. Okay, thank you, ma'am. Thank you.